Good afternoon, ladies and gentlemen, and welcome once again to the live demonstration area. We are very pleased to welcome back Magnum Venus Products. Magnum Venus Products is a global manufacturer of fluid movement and production solutions for industrial applications in composites and adhesive markets. Charles Tur is a specialist in resin transfer molding and infusion technology from MPV, and he will be joined by Alfonso Lopez, an aerospace marketing engineer from Teijin Carbon. They are now going to show us the cutting-edge technique of injection using a grooved silicone bag. Please give a very warm welcome to them. Gentlemen, the floor is yours.
Thank you very much. Hello, everyone. Thank you to come on that demonstration. That demonstration this year is a little bit special. We always focus at MVP on production, helping customer. And here what we show you now is a development. So what you will see here is a part of the development. For that, we work in the collaboration with Teijin because we wanted to produce carbon part. And what we try to do is to offer a solution which is not pre-preg and I will say no low cost, but cheap to produce. So the goal of this development is to produce high-tech carbon part. Inject a part with a minimum of consumable, avoid production mistake, no trimming required. This is the part when it's finished out of the mold. So if we can avoid to trim it, it's a lot of saving time. And fast. We inject that part in 5 minutes. I will do that on the front of you. So this is a silicone membrane details. So we have a groove on the mold. The groove is all around the mold border. We load the membrane inside and we apply the vacuum to seal it. Then we have a vacuum channel to pull the vacuum all around, helping the resin flow. And then we have a collapsible resin channel. So this is the mold how it's designed. We have the mold with the groove. We load the fiber, in this case is a carbon. Then we have a resin stopper. The resin stopper is to be able to help sucking the vacuum, helping the resin flow, but to stop the resin when it arrives on the part border to be sure that resin will not go on the vacuum pipe. Then we load the silicone membrane on the top of that. And as a security, we apply the vacuum on the groove. If you don't apply the vacuum on the groove, it's working. But in production, it's a security. And then we apply a second vacuum on the top of the vacuum channel to assist the resin flow. Then the resin arrives. How the collapsible channel is working. We have a membrane like that. Silicone membrane, 3 mm thick, normal. Groove system, vacuum channel, and the resin channel. Resin channel is working like that. We apply a second vacuum into the resin channel, and when we pull the vacuum, this is what happens. We suck the vacuum into the groove, and we create the groove. In this case, the resin will flow inside the groove. As soon as we finish to inject the part, and even a little bit before, what we do, we stop pulling vacuum, and the membrane comes back at its original position. There is no resin waste. There is no excess of resin, no resin print through on the part surface. So because of that, we can put as much as we like of resin channel to decrease the distance of the resin flow, then to decrease the injection time. So this is the part after we finish to inject. You are not able to tell how we inject the part. So it's working like that. You have the mold, you load the fiber, you load the bag and you apply your first vacuum. Then you apply your second vacuum on the top of that. Then it will collapse. You inject the resin, and when the right quantity of resin is injected, you stop. Doesn't matter where is it, you stop. So for that, we have an injection machine where we have a predetermining counter, so we can exactly program the quantity of the resin we inject, and the rest of the resin that we have on the channel will finish to fill the part. So don't try to inject until you finish. So now, what we do here, we try to reduce consumable, helping the resin to flow. When you infuse carbon, we have two kinds of resin we work with. here we have a vinyl ester resin, but we also work with epoxy resin. Viscosity is not the same. We heat the epoxy and we get like 40 centipoise viscosity. Here we heat a little bit the vinyl ester resin and we have 100 centipoise. It's a little difference, but it can make a big change in infusion. So that's why we decide to help the resin flow by grooving the silicone membrane to help the resin flow. We have different kind of groove according to the resin viscosity. So we do the infusion table test to check the appropriate carbon layup, to test different resin, epoxy, vinyl ester, to check the laminate quality, microporosity, fiber content, and so on, and to evaluate the resin channel size according the layup and the resin viscosity. Then, as we work with epoxy, we have to heat the mold to work on temperature, so we have developed a system which is not new, but we just actualize it, which is a mix of resin and sand around the copper pipe. So this is a silicone bag. If you look at that silicone bag, like many silicone bags, it's flat. So the resin will flow into the injection mat or into a net that you will put, as we do here on the demo with Aerovac, to help the resin flow. Here we don't need it because the resin flow on the little groove that you have on the silicone membrane. So for that we have a special band and we have different size of groove, fast or slow, speed and fusion. We load that, it helps to calibrate the part thickness and then to create the groove on the silicone after building the silicone bag. So then we are able to inject and to check how far it can go. We make different panels, different layup and so on. The part we wanted to test today is a part designed by Alfonso, which is here with me, which is a jet engine hood. It's almost 3 square meters. The form is interesting because it's not so simple as you can see. It's a 3D part design and with some details. So to build the membrane, we have a Patriot Duo system. That was the demo that I ran yesterday. And to inject the resin, we have a MVP Patriot Innovator. We have made a plug. It's a company who make the CNC plug. On the top of that, we have built the mold. So for that, we use a vinyl ester tuning gel coat, a skin coat, and low-profile tuning resin. We use the Euromer resin from the Gazeshim group. Then we put the metal structure. And on the top of that, we build the heating system, which is a cheap heating system, but help to regulate perfectly the temperature. On the full surface of 3 square meters, the maximum difference temperature we have is 1 degree. So that's very good. And we use a mix of resin and sand because we have a good transmission of temperature between the copper pipe. So then we use also a heating system, which is a thermoregulator. So here we don't have it, that's why we use a vinyl ester resin. We use it when we use epoxy. So this is the female mold. On the female mold, before we build the bag, we load the groove headband that helps to calibrate and to create the structure. Then on the top of that, we just build the silicone membrane. So, and we make the bag. And when we demold the bag, after that, we have the membrane. So for that, we have used a sprayable silicone, which is the silicone from Elkem. We have worked with them to develop the right silicone, the right isotropy, the right viscosity, the right gel time. And now we develop with them a silicone that will be more epoxy resistant. The big problem with silicone is the amine that you have on the hardener of the epoxy. So we work on that, and that's the silicone Blue Seal RTV 3724 that we use today with normal polyester or vinyl ester resin. So then we have created the resin channel network to decrease the distance of the resin flow. The resin will flow for maximum 27 centimeters, which is okay. So we demold the bag, we test the bag with the channel, and now this is the part production details. So we have 1 biaxial, 260 grams from Teijin, and 2 quadriaxial. And then on the top of that, we put a Tefloned pill ply, and we use the Polynt resin to inject the part, vinyl ester resin. So for that, we load the carbon with the Aerofix. And I will let my colleague Alfonso to talk about the Teijin fiber.
Is this working?
Please.
Okay. Thank you, Charles. So, as Charles explained, what we're doing here is looking at the first iteration of an aerospace possible process. You know, we all talk about rapid rate, high rate. There is a renaissance in aviation today with uncrewed aerial vehicles, aerial mobility. In this case, what you're seeing is a mock nacelle, so a small engine cover. And we made it with this mold right here in under about 15-minute infusion, which Charles is going to show you. The first layer is a high drapeability, intermediate modulus fiber for stiffness. It's low area weight, and it's going to conform well. We don't have this part up here, but there's no wrinkles. The second thing is we're looking for high fiber volume, and that's where the quadraxial comes into play. We get good permeability, good drape, and then with a thin skin like this, at high rate, we're looking at 55 to 60% fiber volume with epoxy. This is with polyvinyl ester. You can get that here. Charles mentioned the grooves from MVP. This is a process only from MVP, and why we want to work with them, because they can design this membrane for the preform reinforcement and the resin that you're using. Now, in this case, it's too high viscosity. We cannot get that high fiber volume. But if we are looking at an aerospace grade epoxy with the appropriate viscosity, we can easily achieve 58 to 60% fiber volume. That, as I know, is really unheard of in this process. And why we're working with MVP, because for aerospace, high rate, it's not happening yet, but it is going to, and we need to be ready. And in this process, combining the know-how and robustness, which is critical to qualify an aerospace application, is available. This technology is capable today to make an aerospace quality part with 10X material, which we are developing in collaboration with them to, one, make the stitching and drape capability particular to the application needed. Like Charles said, this is a recognizable shape. It's fairly easy to do, but if you start thinking about stringers, ribs, clip components, and as you get larger and larger structures that might combine a skin with a stringer and a wing or secondary part, infusion is a perfect process to make that critical buy-to-fly ratio a lower cost. And that's what we're looking for here. We are looking to lower the buy-to-fly ratio for complex aerospace parts. And this is the first iteration of that. As you saw from the picture that Charles had, we have made 3 parts to date, and that was in 2 days. Nowhere else are you going to tell me that we can make an aerospace part in 2 days. And it has to have the right resin and the right process. And that's what we're doing with Charles.
Thank you, Alfonso. So now we are going to inject the part. So with the camera, you must be able to see the resin flow. So I have the machine connected to the mold. Here I have a vacuum valve. That vacuum valve is connected to the machine. When I start to injection, the vacuum valve will open and will pull automatically the vacuum on the collapsible resin channel. It will open that. The resin will flow first into the resin channel and then into the part. So at the beginning, I create a little bit pressure to fill the resin channel, and after that, I decrease the speed of the machine to let the carbon be impregnated. So, ready? Let's go. Allez. Hop, the resin is coming in. So I predetermining the right quantity of resin, which is 130 stroke. 130 stroke by 39 is something like 5 liters of resin. So now we see the resin coming, arriving here step by step. Yeah. So you see the resin flow. So now I can slow down a little bit the machine. There is no need to rush and to go too fast. And you see now exactly how the resin flow is regular. We are on the full carbon without any flow medium on the top of that. And because of the groove, we control the resin flow. The groove gives 38 grams of resin per square meter, no more than that. So the little line that you see here are the carbon overlap that we have made. So of course we have a little bit more, so it's a little bit longer. So now we pull the vacuum all around the part, so the resin stops here. The resin will fill here. What I have done also, I stop the groove 2 centimeters before the end of the part to equilibrate the end of the resin flow. So there is not much to do. So in this case, what I'm doing, I go to work on my next mold. The machine will stop automatically. That's the goal, to use an injection machine. You have the resin, you mix the catalyst, you control the pressure. We even can use accessories to control the internal pressure to start and stop the machine. So there is nothing else to do. So we are nearly to the end. As you can see here, I will stop, but the part is not finished to be filled. Doesn't matter, I have injected the right quantity of resin. So now what will happen? The resin that we have inside the resin channel will finish to fill the part. That's it. The only thing I cannot forget now is to flush the machine. So what I'm doing, I close by a clamp. If I don't use an automatic valve, it's up to me. Now I put it in, and I flush the machine. Voila. And you will see that. You just have to be patient. Step by step, the part will be filled. Now, just to show you, we have no more vacuum coming into the resin channel. But when I disconnect it, I don't lose the vacuum here. Why? Because I use a special vacuum valve. When I start the machine, the valve open, I pull the vacuum. When I stop the machine, the valve closes. But it's not good enough to close. You have to let the air coming into the resin channel. So for that, that valve will close the vacuum, so we don't lose the vacuum on the vacuum pump, but we have the air passing through. And we have better than that, we optimize that. If you stop the vacuum in once, the resin collapses, so it's a huge quantity of resin, and sometimes at the gravity, that resin comes back in the middle of the part. So we calibrate the air coming in like that, they collapse back in like 2 minutes instead of 2 seconds. So then the resin can flow up. So we leave it like that. Let's continue the presentation. So the resin we use is a Epovia Optimum KRF 4436AI from Poland. A fantastic resin which is designed for boat builder. Normally the gel time is 2 hours, but they set up a gel time of 15 minutes for us, which is nice. We use the different product of Aerovac to load the carbon on the part, and that adhesive completely disappear with the resin, so no mark on the part. And then on the top of that, we put a special, how you call it, a special pill ply, which is Tefloned pill ply, very easy to remove. So the injection time depends on the viscosity of the resin, temperature of the resin, and the resin layer. So now when we demold the part, I'm not able to do that now, but you can see what happened. I remove, I have all the groove on the surface, my membrane is self-cleaning, so we don't see anything. And then I remove very easily the Tefloned pill ply. So then, this is the part I get. Another thing, and as you can see on the part, we take the time to load precisely the carbon. So for that, when we design the mold, we make a mark or a step on the part border. So instead to trim the part, we take the time to load the fiber on the right position. Like that, when we demold, there is nothing to do. So it's better to, to use time to load properly the glass than to trim the part after it. That creates a lot of dust, especially with carbon. At MVP, we do organize training. So we do training all around the world. Here, for example, we are in Egypt. A customer who works for transportation. We were running light RTM and silicone membrane flex molding training. We do that with our distributor, again, all around the world, which is here in Mexico. Then we have 2 training centers, one in France, in the south of France, near Perpignan, and the second one in Knoxville, Tennessee. Our next school training will be 3 days, the second week of April, in Tennessee. We would like to thank very much Pauline for the resin, Elkem for the silicone, Aerovac for the raw material, GEC for this fantastic organization. If you have any question, we can introduce everything to all of you on our booth, which is 5U58. Feel free to come. And now, if you have any question, we're here for you. We have 5 more minutes. I was too fast, sorry.
Are there any questions for Charles? Thank you, Charles. If you have any questions, please don't hesitate. We have a mic here.
Don't try to let me know you understand everything with my English.
It was perfect. Please feel free to come and discuss with Charles any additional questions that you have, or visit the team at the MVP booth. They will be more than happy to answer all of your questions. Ladies and gentlemen, the next demonstration is happening in just 5 minutes with McLaren Composites right here on the live demonstration stand, so don't hesitate to stay, and otherwise enjoy your afternoon at the Czech World. Thank you so much.